We've talked about a number of features of cameras, about how to focus them and how an image is formed on a screen or a film, and how that's related, how the location of the image is going to be related to the focal length and the location of the object. And we've also talked about camera magnification. I wanted to see some of these things play out and actually try to understand if how what I observed matches with some of the equations we've written down. So I decided to make a very simple camera in my office. My camera was going to be looking at an object, a source of light, which was actually going to be a light bulb. Light bulbs, of course, just have, besides being a glass bulb, have a little filament inside them that glows bright hot. So that's what I was going to be taking a quote-unquote picture of. My camera was going to be nothing other than a lens. I started out with just a styrofoam cup, and I jammed a piece of glass lens, into the bottom of the cup. I didn't have film for this camera. I just used a white screen, a piece of paper, and I looked at the image that was formed on the white screen. Of course, since cameras make real images, I expected to see a projection on that piece of paper, and I expected it to be inverted, much like a real image is supposed to be. And what I decided to do is measure how far the object is away from my lens and see if the image distance that's formed it matches up with our equation that we've been so familiar with. So here's my camera in my office. There's the light bulb that I'm going to be observing, clamped to the edge of the table. There's my camera lens jammed into the styrofoam cup. So light source, lens, and there's my screen. That's what would be film if I had an ordinary camera that could take away pictures. But I'm just going to try to project an image onto that screen. When I turn the lights out and just turn the light bulb on, then this is what I see. The light bulb is glowing nice and bright, and I start to see an image form on the screen. This one happens to still be kind of blurry. But I started making notes for myself about what the object distance was, and I started making recordings of the lens distance to the screen when it was that I finally got a sharp image. In this particular case, I still had an image that's blurry. And it turns out I had to keep moving the screen further and further back. The image got sharper the further away I moved the screen. But finally I found the right sweet spot. Then the image became very sharp. It became so sharp, in fact, I could start to see the filaments of that bright light bulb, and you can see them here in this picture. So I just took my camera, my ordinary camera, my SLR, and then took a picture of that screen. So I took a photograph of that white paper in the previous picture. You'll notice the filaments of the filament coils inside the light bulb. And you can even see the holder that keeps the filaments stationary inside the light bulb. There's a little metal L-shaped holder. The image turned out to be upside down. It's inverted like it's supposed to be. And for this particular case, where the lens was really close to the original light bulb, the image turned out to be huge. It was really magnified. In fact, it was so big that it was more than the size of the piece of paper. This was the only part of the image I could capture on the sheet of paper. That actually makes sense because I remember that the magnification gets big whenever the object is rather close to the focal length. It was upside down, it was inverted. That was good because it's a real image. So I decided to graph this. I was going to graph the image distance, the distance to the white paper that I had to move the paper to in order to get a sharp image, as a function of the object distance, the distance between the original light bulb and the camera lens. And I was going to take several measurements at different locations. The particular one I just showed you, it turns out that I had to move the screen very far back. I had to move the paper way behind the lens. The lens distance to the original light bulb was only 22 centimeters, but the lens distance to the image turned out to be 92 centimeters, almost a meter. So that's graphed right here. On the horizontal axis, the object distance is 22 centimeters. The lens to image distance was 92 centimeters. Then I made a slight refinement on my homemade camera. Instead of a styrofoam cup, I took a piece of cardboard and I stood it up perpendicular to the table with a little stand, and I taped the lens inside of it. So there's my light source again, there's the lens, it's taped inside of a cardboard holder. That's because in my previous picture there was a lot of other light reaching the screen besides the light that was passing through the lens. So this little adaptation here made sure that the only light reaching the screen was light that actually had to pass right through the lens and get to the screen. So that makes a nice shadow of everything else, and the only light should be the light coming from the image. So I again measured the object distance. I measured the image distance when I finally got a nice sharp image. And here's what I saw. Now I have a nice sharp picture, and the only light reaching the screen. Now I have a nice sharp picture, and the only light reaching the screen passed through the lens. You can start to make out a lot of features of the light bulb. Here again are the filament coils inside of the light bulb. You can see that nice little metal holder that keeps the filament stationary. And you can notice the glass of the light bulb itself. As we noticed the object distance growing, in other words, I moved the lens further back away from the original light source, the image became smaller, and I could start to fit the whole image onto the white screen. It was still upside down, in other words, it was inverted, and that should be because it was a real image. And here's what I saw as I moved the object further and further away from the lens. A number of different points where I plotted the object distance and the image distance. And notice how the plot looks. It looks like the further and further away I move the object, the closer and closer the image distance approaches about 21 centimeters. That's not surprising because it's just trying to approach an asymptote. That turns out to be the focal length. How do I know that? Well, remember that the equation is 1 over p plus 1 over I equals 1 over f. As p becomes infinitely big, this first term goes to 0, and 1 over I just equals 1 over f. So that's what should happen. The closer and closer, well, the further and further I move the object away from my camera, the further I'm trying to zoom out to reach something further away, then the image distance approaches the focal length. Also notice that the data doesn't really, it takes off as I start to get closer and closer to 21 centimeters on the object distance. That's because it's harder and harder to make an image when the object is too close or closer than a focal length. Your camera is probably similar at home. An object far away from the focal length of the lens is not magnified very much, just like mine wasn't. And an object as it nears the focal length becomes more magnified. And furthermore, if the object is too close, you can't get an image at all because you can't be inside the focal length and still get an accurate real image.